So this is a question that's going to ask us to find the current through any and or all of the resistors. So find all currents through each resistor. And as you can see, we have resistor 1, resistor 2, resistor 3, and resistor 4. We have our EMF here, our voltages at 12 volts. Resistance 1 is 2, resistance 2 is 4 amps, and then resistance 3 is 3 amps, and resistance 4 is 2 amps. Something that I like to do right off the bat is we're going to call resistance 3, 4, which is a combination of them, 5 amps. And the reason we can do that is because these guys are in series with one another, so that they can combine, meaning that the equivalence resistance is the sum of the two. No inverses needed, because that would be for if they were in parallel. So the first thing we need to do is draw our loops and our currents. This is probably the most important thing. I'm going to just I always do my loops the same way. One loop that way, one loop this way. And I'll tell you why that's important. It's really important for determining positives versus negatives in both our voltages and our resistance. Now we draw our currents. We have 3 different currents. Again, I always do this the same way, and I'll explain why. But I wish I had a little more space, but that is going to be our I1, so our current 1, and he's going this way. Then we're going to do our current 2. That's going to be our I2. He's going that way. And then starting here, all the way down, that's our final I3. The reason I always do them this way is so I can keep this small formula the same. The formula being I1, current 1, is equal to I2, current 2, plus I3. I'm going to circle that because we're going to use that later. The reason this is because whatever's going into our first junction has to be equal to what's coming out of our second junction. Current 1's going into our first junction, current 2 and current 3 are going out. Therefore, I1 is equal to the sum of I2 and I3. This current's going into junction 1, this current's coming out of junction 2, and as is I3. So you can orient these different ways, but you have to change this according. So I like to keep it the same so I can always have the same formula. Regardless, I think you should understand why you have to have it the way it is. Okay, the loops help us to dictate, the loops in relation to our current help us dictate whether we're going to be working with positive or negative numbers. If they are going from a low to a high voltage, then perfect, or negative to a positive, like this would be the negative side, this would be positive. Low to high, I just like to say that's going to be a positive voltage. If the loop in the current are going the same way for resistors, so this one's going this way, this is going this way, same way, it's negative. If they're opposite, it's positive. We'll see that later. So I like to break it up into left side and right side. Left side. So we're just looking at the left side here. No right side right now. What do we have? We have our volts, okay? As we said, it's positive. It's going from a low to a high. So we have 12 volts. And again, we know that our I multiplied by our R is equal to our voltage. The way we have our positive and negative, we can put them all on the same side and set the equation equal to 0. So we have our 12 volts. That's the first thing I do. Then I look and say, okay, resistance 1 and current 1. This loop's going this way, this is going this way, it's got to be negative. So we have our I1 is the current that's working with R1. So what it's going to be is it's going to be negative because it's the same way, and it's going to be I1, which we don't know, multiplied by R2, which is given as I1 multiplied by R1, which is 2 ohms. Then we have one other thing in this left-hand side. We dealt with this. Now we just have to deal with this. We look at I2, and this loop, same way, it's going to be negative, and that's our I2, because that's the current that's there, and that's being multiplied by 4 ohms, because that is our resistance too. So that's everything we have for our left side. So I'm going to just circle this too, because that's our derived equation. Now let's do our right side. Again, so we don't have to, on this right side, we don't have to deal with any volts because we only have EMF over here, whereas the voltages, there's no volts over here, which makes it a little bit easier. So what we have here is we have, I like to start down here. We combine these as, and they're going in opposite directions, so they're going to be positive. So we're going to call this R, we're just going to call it R3. So the combination of these two is called R3 because we combine these by adding them in series. Therefore, we have to use 5. Sorry, this is I3. I3, and then R3 is the combination, so that's 5. So that's an I. And then we have one more to take into account, that's it. And these are going the same way, so it's a negative, and that's going to be our I2. And then what's our resistance? It's 4 ohms. So it's as simple as that. I'm going to rewrite this because I sort of messed up. Our right side is I3 multiplied by 5 minus I2 multiplied by 4. Okay. So in my opinion, this is the hard part, getting to this point. Understanding our currents, understanding what's positive, what's negative, understanding our loops, how they correlate with positive and negatives, understanding where they go into junction 1, where they come out of junction 2 to get this guy. So with these 3 equations, I mean, each one's missing at least 2 variables. Therefore, we're going to have to do some substitution to find any and all of the currents through either of the resistors. So how we're going to go about this. There's honestly a couple ways you can do it. So I'm just going to look at putting I1 in terms of I2 and I3. So we're going to do our left side equation, and we're going to go, okay, 12 volts, that's given, right? Minus, okay, here's our I1. I1 is equal to I2 plus I3, therefore we can put that in and distribute. I2 plus I3 multiplied by 2, and then just keep our I2 and then our 4. This works because I2 plus I3 is equal to I1, therefore we can put that in. Let's distribute our negative, and then we're going to distribute our 2. We know that's volts, I'm just going to keep it as 12 to keep it easier, and that's going to be minus 2 I2 minus 2 I3 minus 4 I2. Okay, so now we have a couple like terms. Perfect. 12, let's negative 2 minus 4, because those are both I2, minus 6 I2 minus 2 I3. Okay, awesome. Now we can solve for one of them. What we can do is, there we go. We can put, let's put the 12 on one side, and then let's do the 6 on the, or let's just move this negative 2 on the same side. So add 2. So now we're 2 I3 is equal to 12 minus 6 I2. Now let's just divide by that 2. So then 12 divided by 2 is 6. 6 divided by 2 is 3. So awesome. Now we have an equation or a formula for I3 in terms of I2. This is a 2, bad handwriting. So now what we can do is we can look at, and again, I'm going to circle this because it's a final point. We can look at our other formulas that we got earlier. And we have, if we have one with I2 and I3, that's perfect because we can plug in we can plug in for I3 in terms of I2, and therefore we only have I2s. So we're going to use this guy. So it's our I3 multiplied by 5 minus our I2 multiplied by 4. So that's all that is. So that was we got that earlier from our circuit. So now let's plug in our, this because it's equal to I3. So 6 minus 3 multiplied by I2 multiplied by 5. And then just keep our I2 multiplied by 4. So now let's distribute this 5 in. We can do 6 times 5, obviously. So then we're doing 30 minus 15 I2 minus I2 times 4. Let's combine our I2s. So it is, it's a negative 4 I2 minus, so we have a negative 19 I2, and then that's 30. Subtract the 30 over to the other side. We'd have a negative 30 is equal to a negative 19 I2. So then 30 divided by 19, it's a negative 30 divided by a negative 19. I2 is going to be equal to 1.578. So that's our answer. That's the hardest part. Obviously, that's the majority of it. It asked us to find the current through different resistors, and the current for resistor, or the current 2 is going to be 1.578. And the way we can do this to find others is just by plugging this in. So now that we have I2, we can plug I2 in there. 1.578 multiplied by 4. And then let's subtract that to or add that to the other side because it's negative, and then divide by 5. I3 would be 1.26. Now we go up here, we have I1 and I2. So we already know I2, so why not plug, and again, we also just found I3, so we could also do this. I3 plus our I2, which is 1.578, is equal to our I1. So I1's 2.84. So once you find one, you can find them all. So those are each of the currents through different resistors. And you can find what resistor it's through by the number it correlates with. So because this is 4, we know it came from resistor 2. So current through resistor 2, that's the resistor it's through. Our 1 was, I suppose we found I1 through this, but this current only runs through resistor 1, so that's the current at resistor 1. And then R3 is the current at the combination of these two resistors. So that's the end of the demonstration on how to find currents through multiple resistors. It's just, the hard part is finding that first one, and then it's just plugging and chugging for the rest. So yep, that is everything.